Welcome to the Energy Club's faculty series of presentations. And today we have with us Dr. Jeong. Hope I'm pronouncing that right.
Correct.
He and two other professors are currently all working together to develop different carbon capture membrane technologies, particularly for the Advanced Research Projects Agency for Energy, which is a high-risk, high-payoff energy development agency. So let us please give a warm welcome to Dr. Jeong.
Thank you very much. It is my pleasure to talk a little bit about the kind of work that we do, again in collaboration with you in chemistry as well as Professor Paula Balbuena in Chemical Engineering Department. The title of my talk today is, again, the work that we do, supported by ARPA-E, which is about post-combustion CO2 capture by stimuli-responsive metal organic frameworks. Okay? So, before we talk more about this and acknowledgement and things like that, I'd like to know a little bit about you guys. Okay? Guys are mostly grad students, not necessarily. So, and probably not you, probably, sir. Undergraduates? Okay. Okay, all right. Mostly aerospace engineering?
No,
not necessarily.
Mostly engineers.
Engineers, okay.
With a handful of.
So aerospace engineers, okay. Mechanical, civil, chemical, electrical. Oh, cool. Okay. Biomedical? No. Okay.
I'm petroleum.
Petroleum. Okay, good, very good. So, again, for those, I always like to have this slide here, okay, which is kind of interesting. Whenever I give a talk to first-year grad students in chemical engineering, you always start with a very, very high ambition, and then it turns out that we can actually model this exponential function, right? It drops exponentially. And you start with the same word, here I come, okay? My goal is to get the Nobel Prize. And then by the time you graduate, you're saying the happy hour, here I come, and I'm happy with the pepperoni pizza or whatever. Okay? So keep this in mind, okay? You really have to start with a very high ambition, okay? And you know that, okay, your ambition will gradually, depending on the, okay? So, yeah. Again, I'm co-PI, one of the co-PIs. At least, truly, we have a big sort of a team of researchers, including chemists. A lot of chemists, by the way, a lot of chemists, and then a chemical engineer who is Professor Balbuena is primarily focusing on the computational side. And my contribution is to the first measure the CO2 and CO2 nitrogen absorption capacities as well as the gas transfer properties in this type of materials, and then develop membranes out of these materials. Okay, the work is supported by ARPA-E, and this is our second year. And as Nicole just said, this is high risk, and which means it's challenging. It's not that easy to meet the expectations. But anyway, so I talk a little bit about motivation, why we do this research. I'm going to focusing on climate change issue, and then we're going to talk about I'm going to talk about post-combustion CO2 capture, the primary system challenges, and then I will talk a little bit about this again, stimuli-responsive metal organic frameworks and the powder as particles. For absorption-based CO2 capture, and then spend some time talking about how we synthesize membranes and what are the challenges and what are the issues associated with it. And I will summarize my talk today. So, if you take a look at average temperature of the globe, back in 1884 versus 2006, you can clearly see that. On average, temperature of the globe has been increased, and we can see, whether you may disagree with me, but this summer somehow Texas, we have record high temperature in Texas, could be potentially associated with the climate change as well. And if you take a look at the glacier, the amount of glacier in Mount Kilimanjaro in Africa, this is 1993, this is 2000. Okay. In fact, that the 87% of the glacier in this mountain has been disappeared since early 1900. Okay. So this is a serious issue. Again, we all know that one of the major source of this greenhouse gases, obviously, CO2, and one of the major sources is fossil fuels. Okay? However, fossil fuels, okay, will continue to be a major source of energy. Okay, petroleum engineer, don't worry about it. Okay, your jobs are secure for a long time. So this is basically energy. Again, this is energy outlook published by DOE 2010. As you can see here, we are right here at 2011 here. The x-axis is basically the port BTU. And we can see that the portion of nuclear is pretty much saturated. Natural gas is slightly increasing, and coal is still there. And then we have liquid hydrocarbons. We do have substantial increase, expected increase in the renewables, but still the relative portion of the entire energy required is still minor. Okay? So we're gonna use fossil fuels no matter what. Okay? So if you take a look at the CO2 generated per kilowatt hour power, coal. If you use coal, then we generate almost double, twice as much as CO2 by generating electricity by gas. So CO2 generation from coal power plant is problem. So it turns out that coal-fired power plant is a major anthropogenic carbon dioxide source. So if you take a look at the total CO2 emission, US emission, okay, in 2026, we have 6 billion ton. And out of 6 billion, 40% is coming from electricity sector. Okay. Out of this 2.3 billion ton coming from electricity sector, okay, coal-fired power plant is responsible for 83%. Okay. 1.9 billion ton. And also we have a growing economy, China and India. Okay. As their economy grows, their power demand will go up, and the CO2 will generate even more. That's a problem. And it turns out the US has the world's largest coal reservoirs. 27% of the coal is right underneath, okay, in our soil. And China is the top producer of coal, 38%. And now, what does this mean? This means that most of the oils that we import are coming from the countries that are politically not stable. Okay, we have 27% of world coal reservoir right underneath our soil. So if we can somehow find a way to, use coal, without generating too much carbon, okay, with the carbon capture technology, then that's truly, beneficial not only for country energy demand, but also for political, things. So this is a really serious problem. Again, if you have any questions, please stop me, and I want to have this presentation as informal as possible. So we have there are 3 different ways to capture CO2 from coal-fired power plant. Okay, one is basically post-combustion, which is basically you have an existing power plant, okay, and you basically you add a CO2 capture unit to the existing power plant, and you basically capture CO2. This is called post-combustion. pre-combustion is different. Okay? So you have gas shift reactor here. However, we have a air separation unit here, and you basically separate air, oxygen from nitrogen, and you basically burn fuel with oxygen, okay, to convert fuel with oxygen to have a hydrogen and CO2, and then you capture CO2, because now here you have 40% CO2 versus only about 10% CO2. So it's a lot easier to capture CO2 here, as well as we don't have nitrogen here, in theory. So separating CO2 from nitrogen is a lot more challenging as compared to separating hydrogen from CO2, or CO2 from hydrogen. Okay? So this has a certain benefit. And oxy-combustion is much more complicated, but okay, generally, this is also has again air separation unit. Okay. Now it turns out that the post-combustion capture is most attractive. Okay. Here's why: because this process can be retrofitted to the existing coal-fired power plants. Okay, all you have to, in theory, in principle, all you have to do is basically build the additional unit. Okay? And turns out this is a leading candidate for gas-fired power plants, and also offers flexibility, okay, which means when the capture plant shuts down, the power plant can still run. You don't have to shut down entire power plant. And obviously, during, while you're repairing the capture unit, okay, you basically have to release CO2, but you don't have to stop the entire plant. However, the other two, pre-combustion and oxy-combustion process, are too much integrated, which means if something goes wrong with the capture unit, then you have to stop the entire plant. And also very slow in commercialization of pre-combustion process, which is called IGCC in US. Okay, this is again the reason is because it's very expensive to build, and so that's the major issue. Now, what are the challenges? Okay, challenges are following. The flue gas is dilute in CO2. Okay, what does that mean? That means you have 80% or above, 85, 87% nitrogen, and you have about 10% CO2. Okay, which means you have very little driving force. Okay, for membrane, for instance, or even for adsorption. Okay, just because you have so many nitrogen in this room as compared to CO2. So in order to capture CO2, it's a little bit energetically, it's not favorable. Again, because of this, like I said, significantly higher performance or circulation volume required, and CO2 produced at low pressure compared to sequestration requirements. Okay, which means you really have to, after you separate, you really have to repressurize in order to sequester this CO2. So this is how, go ahead.
What temperatures are commonly seen in flue gas?
Typically they're talking about 40 Celsius. Okay, depending on the operation, I suppose, again, the gas temperature that is coming out from the stack, okay, is typically, can be assumed as at 40 Celsius, okay, 40. So this is how the schematic illustration, how the CO2 is generated CO2 captured in post-combustion capture unit. So here you have a coal. You see this coal is dirty, by the way. It's not just carbon. Like you have carbon here. Carbon is only 50%. And a lot of water, and oxygen, ash, and hydrogen, and sulfur, and lead. Mercury, I'm sorry. Okay? So these are coal. And then you have air, and you oxidize, you burn, okay? And then you basically generate steam, and steam will generate a turbine, and turbine will generate electricity. And typically, before you capture CO2, you generally capture SOx and NOx first, okay, as well as particulate. And then if you have this, this is typically the flue gas composition right now, so 10% or less, depending on what kind of coal that you use. 80% nitrogen and about 10% water, and